So the other incredibly important concept we will need when you're in a rotating framework is angular momentum, right? On Earth we are rotating and then you are moving around in the atmosphere or the ocean. Then there is this concept of angular momentum, which I'm sure you've been exposed to in a physics class or so. And all it says is that the angular velocity times the distance from the axis of rotation is conserved if there are no frictional effects and so on. So assuming this frictional forces are not important, the non-rotational framework velocity times the distance at any point in the tank, that parcel of water, has to maintain its angular momentum, so that product has to be constant, and that is equal to omega r1 squared, because our tank is introducing water with this pump at the edge at r1, and the water parcel that comes in has got omega r1 as the initial angular velocity before it starts moving towards the drain. So the angular momentum would have been omega r1 times r1, so omega r1 squared, right? Remembering that the non-rotating framework velocity is v theta relative to the tank plus the rotation of the tank omega r. We can multiply this with r, so v theta r would be omega r1 squared, so multiply by r and replace it with omega r1 squared, and we can manipulate that equation then as omega r1 squared equals v theta r plus omega r squared, and then we can solve for v theta instead of in terms of omega r1 squared minus r squared divided by r. What does this mean? This means that the r1 minus r is going to increase as the particles move towards the drain, and the velocity is going to be scaled by r. As the r gets smaller, it's going to get faster and faster, as we had seen the dependence on the rotation rate with two different rotations. That's kind of what this is saying. So there is a scaling with respect to the distance from the axis. Okay, this becomes critical because on Earth it's a sphere, and we'll see that as you move from low latitudes to higher latitudes, you are getting closer to the axis of rotation. So this scaling of r is critical. Okay, so that's kind of in the water tank. Now we have to transfer it to the sphere. So let's first look at the rotating coordinates themselves. How does a parcel that's not anymore balancing forces in a non-rotating framework change when we do things in with rotation? What is the most important thing? The thing to remember here is, here again is our inertial reference frame velocity, but in the rotating framework with rotation omega r and radius r, you have omega r, the rotational speed itself, and u with respect to the rotational framework to give you the total inertial frame reference velocity, right? So here you're carrying a unit scales, unit vectors sorry, in the x, y, and z direction. The difference being, so on the real sphere, we're going to make this the longitudinal direction, the latitudinal direction, and the local vertical, as I mentioned already in another context. This itself is going to move, which means they are not constant. Like ijk we use in the non-rotating framework problems in physics, we will have to worry about the changes in the unit vectors themselves. That's going to be kind of leading us to the rotational effect on the sphere. So u inertial is again u rotational plus omega cross r. Omega is a rotational vector, r is the distance vector. So it's the u in the rotational framework and the velocity added by the rotation itself. So any vector a can be written as unit vector x times ax plus y hat plus ay plus z hat az, where ax, ay, az are of course components in each direction. Then the total derivative of dA of a is going to be dA dt in the rotational framework. We will slowly just move into the rotational framework because all the dynamics we do on Earth and ocean and atmosphere is obviously rotational framework. So in a non-rotational framework, you would just have x dAx dt plus y dy dt, z dAz dt, because x, y, and z would be unit vectors that are not changing. But in a rotating framework, since they are moving, if you look from the inertial framework, then the x itself is moving, so dx dt has to be taken care of, and in the inertial framework there will be omega cross x, dy dt is going to be omega cross y, dz dt is going to be omega cross z. So if you are sitting on the rotating framework, you are like we are sitting on Earth. Earth is rotating, but we don't feel it, right? Because we are sitting on Earth and moving with Earth. But if somebody was standing outside and looking in, like your mother standing by the merry-go-round and looking at you going around, then this is the equivalent. In the inertial framework, dx dt, dy dt, and dz dt have to be taken into account, which are omega cross x, omega cross y, and omega cross z. So going back to our vector a, then doing the total derivative in the inertial framework is going to give us x dx dt, so this is the regular term we would have in a non-rotating framework, plus dx dt times ax, so just the law of partial differentiation, dy dt ay, dz dt az. Okay, so together what do we have? X dAx dt, y dy dt, plus z daz dt, plus omega cross x ax plus y ay and z az. What did we do? We basically used the fact that dx dt is essentially omega cross x, right? It's just the rotation that is changing the unit vectors in time. They're just moving in time, right? So we use that simple relation. We use this relation in here to write dA dt in the inertial framework as this term plus this rotational term. I think you're getting the idea. That's how you end up with dA dt in the inertial framework as dA dt plus rotation, dA dt in the rotational framework plus omega cross A as the total. Okay, so we will have to look at this in a bit more detail and then add this on a sphere. That's what begins to make it just a tiny bit more interesting. So just make sure that you follow